and welcome to everyone. As Claire mentioned, I've actually been working in positioning mobile phones in a variety of different ways for getting on for 10 years now, and wrote some papers 5 years ago on how to bleed every last drop out of Bluetooth, which I'll explain some bits on through the course of this talk. And I'll explain why Bluetooth isn't going to be the solution here for contact tracing apps, and the things that we need to add to that to make them really robust. So in the course of the talk, I'll give a quick recap on what contact tracing is all about, and then explain the problems that have been coming up over the last few months with digital contact tracing on smartphones, and explain how we're going to try and fix this in the future. So a quick reminder on how contact tracing works. I'll get my little red pointer up. The idea of traditional contact tracing, manual contact tracing, was that when someone was determined to be infected with something, a human being would speak to them about who they'd been in contact with recently and where they'd been. That human contact tracer then would go and do the detective work of trying to track down not just the people who the original person already knew, but all of the other people that they didn't know as well, like the person that sat next to them on the bus yesterday and all that sort of stuff. So traditional human contact tracing is a real deep piece of detective work that in the past has relied on good knowledge of where people have been and as much information as they can provide on who they've been with as well. The idea being that you can track those people down and encourage them to isolate before they themselves start to shed the virus. And so the original opportunity for digital contact tracing, i.e. using our smartphones to help, was to simply help the traditional human contact tracers. So your phone can keep a log of where you've been. You could choose to turn this on and off. There are plenty of apps that already do this for you. And your phones can talk to each other in the background, even while they're in your pockets or in your bags, and share IDs, and therefore keep a log themselves as to which other phones they've been near and when. But there is this other aspect of everyone's privacy, which of course has to be respected as well. And we don't live in utopia. So people will try to do malicious things with apps that can gather data on where people have been and things like that. But privacy is something that is naturally counter to contact tracing. If you take privacy to its extreme, the kind of questions contact trace ask, like, please tell me everywhere you've been in the last 2 weeks and who you've met with, the ultimate privacy providing answer is no, mind your own business. So we have to try and strike a balance between these two things. The technology inside our phones that can easily be brought to bear quickly is Bluetooth Low Energy. So this is a radio signal that's used in phones at the moment to do things like talk to wireless headsets and communicate with smartwatches, and to share information between two smartphones, like share a contact and things like that. I'm sure most of you have used Bluetooth yourselves at some point. So every Bluetooth, this is a screenshot of a simple Bluetooth scanning app, just to show when you fire off a Bluetooth scan, all of the sorts of different devices you can detect. Now, you'll see these funny little code words here with colons in them. That's the unique identifier that every single Bluetooth radio has. So they already announced their unique identifier, and your smartphone already tells you the signal strength of the device it can see. And there's this rough approximation that a high signal strength means that you're nearby another device. And we'll certainly dig into that aspect through the course of this talk. But one of the first things people were concerned about was these unique identifiers, and the idea that if you're going to log them, you might be able to identify the original person through that identifier. And so people immediately started figuring out privacy preserving techniques to anonymize the Bluetooth information. And the first fight broke out between people who were promoting decentralized versions of privacy preserving techniques and people who were promoting centralized versions. And the key difference between those two is whether the information is being managed, stored, and passing through some central location, like a server within the National Health Service here in the UK, or a decentralized version where the only central point of contact that the smartphones communicate with is a simple rerouting service that passes messages between the phones, and it doesn't actually store anything at all. And there are pros and cons of both of these approaches. So a decentralized approach is inherently higher in privacy because there is no central computer doing any processing or storing any data. But that means that because there is no central computer doing any processing or storing any data, you can't easily do any data analysis. And data analysis is very useful. There's a whole host of things that you can do. You can confirm whether the algorithms you're using are working well. You can develop new ones and test them on old data before rolling them out. You can correct mistakes, like contacting people again after a few days to let them know that they were incorrectly contacted the first time and can unquarantine themselves. All sorts of benefits of having the data, including understanding the spread of the contagion across the country and having a regional understanding of who's using the apps and who isn't, and all sorts of things like that. But of course, the con is indeed privacy, data breaches, loss of the data. And of course, we now live in the GDPR age, so that is a challenge as well. And so there's basically two camps, and still two camps, different smartphone apps going down different roads in terms of whether it's centralized or decentralized. Then in April, there was this announcement that a partnership was taking place between Apple and Google to try to aid with contact tracing. And to my knowledge, it was the first joint venture, if you like, between Apple and Google on some major new technology. So it's very exciting when it came about, but it's certainly not been without its challenges. And then the second fight broke out. So this is all to do with how the Bluetooth data is being used. And the old scheme, the old API calls that have been around for a long time, basically give the user, the contact app builder, much more flexibility and much more capability than this new protocol that Google and Apple have developed. And I'll let Matt Hancock explain the problem, and then I'll explain where it's come from.
We found that our app works well on Android devices, but Apple's software prevents iPhones being used effectively for contact tracing unless you're using Apple's own technology. So as it stands, our app won't work because Apple won't change their system, but it can measure distance, and their app can't measure distance well enough to a standard that we are satisfied with.
So that's quite a quandary. So there were two key problems there. The first one is that using the traditional schemes doesn't work properly on iPhones. Using the new scheme, the NHS were not happy that it could work as well as they could develop on their own. And the first problem is quite a simple one. The iPhone has been well renowned for its good battery life for many years, and it's something they're clearly very proud of. And one of the things they're doing to enable good battery life is putting the phones into a deep sleep mode, basically, when they're in your pocket, and they turn off as much as they possibly can. And one of the things that they turn off is the ability for the Bluetooth radio to detect and hear other devices trying to talk to them over Bluetooth. And that basically means that using the old Bluetooth API calls renders the iPhones effectively invisible to contact tracing when they're asleep in people's pockets, when they're not in use, which of course is a major problem. The challenge though, as Matt Hancock, the health secretary here in the UK, stated there, was that the new protocol that Apple and Google have built is not as good at detecting distance and therefore exposure to the virus as the old scheme is. And we can dig into why that is the case. So the Bluetooth measurements that we have on smartphones, we can only use signal strength to try to estimate range. And this already is a problem. No one develops a signal strength only positioning technology. It's not a good idea. You want to use ranging measurements, time of flight measurements. This is already well known and well understood. And Bluetooth was not designed for that purpose. It was designed as a communication system. And so all we have is the signal strength to go by. Now, the idea is that the further away you get from another device, the more the signal strength goes down by free space path loss, which is a well understood bit of physics. One of the first glaring problems you get is that Bluetooth signals at 2.4 gigahertz are stopped relatively well. They're attenuated quite strongly by big bags of salty water. And big bag of salty water is what physicists like to call human beings in their models. And this is a experimental bit of data of walking away from a Bluetooth transmitter with a smartphone versus walking away from the same transmitter in the same manner but with the phone held the other side of your body so that your body is in the way. And what this complicated looking graph is telling you is that putting one body in the way adds about 10 meters to the apparent distance. So you can be stood half a meter from somebody, put the phone behind your back, and the contact tracing app might think that you're now 10 meters away instead of half a meter away. So that's a serious problem that's to do with the frequency that Bluetooth is used at. And so that can provide false negatives to the system. It's also possible to be very close and measure a very high power, but not actually be at risk of contracting COVID-19. So being the other side of a pane of glass, for example, and not actually breathing the same air. And this is false positives, a contact tracing app reporting that you were with somebody that you were not with, you were the other side of a window. But one of the simple things that everyone would like to be able to do, at least exploit, is that it should be impossible to be very far away and detecting a very high power. You should only be able to detect high powers when you're very close. But in practice, this is not true. And this is a very surprising initial result that is in one of my papers. I'm going to be explaining some of the findings from my papers, and you can, the links are at the bottom there. But this is walking away from and then back towards a Bluetooth transmitter. It's all real data gathered on a smartphone. And these measurements that all seem to be very high, as you can see, there's a -30 there and a -30 there. That represents higher power than the other transmitter was even capable of transmitting at all. So there's something clearly very wrong here. And the other thing is this other population of measurements has a very large spread of errors. And the typical casual observation when people start getting into the Bluetooth positioning game is they look at these sorts of results and they just go, oh, it's cheap equipment, the signal's very noisy, so we should just do averaging. But actually, if you dig into the causes behind these things, you can understand where they're coming from and remove them in a better way. And as you'll learn in a few minutes' time, averaging is the wrong thing to do. And yet that's what most people assume they should do. So I've mentioned the impossibly high noise levels. This spread here is actually 10 times greater than the actual noise level you expect to see on a Bluetooth measurement. So something's very wrong with these real data gathered from real smartphones. The first very high value problem turned out to be crosstalk between the Wi-Fi in the smartphone and the Bluetooth radio. So in effect, when your Wi-Fi is screaming out some email, or you're watching YouTube or something on your phone at the same time as trying to do contact tracing, you can inject power from your own Wi-Fi transmission back into your own Bluetooth signal strength reading. And so turning off the Wi-Fi on the phone removes these spuriously high incorrect values. And you definitely want to remove them, because obviously if you're really quite a far distance away and you get some spuriously high values, you'll look like you're much closer than you really are. Now, app developers can't easily be flicking the Wi-Fi on and off every time they want to do a Bluetooth reading, but the operating system developers can choose to do this. So it's the sort of thing that needs to be built into the Google Apple exposure notification protocol. So be aware of that. And if app developers can't be turning off the Wi-Fi while trying to do contact tracing, then you have to gather enough data to be able to detect and remove spurious, incorrect, high-value measurements. Now, the next problem, the big spread in apparent received power, is caused by a behavior to do with how Bluetooth works at all. So this is the 2.4 gigahertz radio band. It's shared with Wi-Fi, and there are 40 Bluetooth channels spread across the band. And these ones labeled 37, 38, and 39 are what's called the advertising channels. And they're the channels that Bluetooth devices use to say hello to each other on. And they hop between those channels and transmit a hello message on each of these different channels in a constantly hopping sequence. So if you make a special device that can only transmit on one channel, and smartphone apps can't control this themselves, you can't write a smartphone app that only transmits on, say, channel 37. But if you make a device that does, and then you use a smartphone to record data from it, you will actually see the very low noise floor, the about 2 dB standard deviation noise that you should be getting, which is about 10 times lower than what you detect when you use a different smartphone. Now, if you start using a special device to just look at these individual channels in turn. So a smartphone has gathered this data, but only channel 37 was being transmitted, and then only channel 38, only channel 39. This is a static test, and yet the different channels are giving quite different power at different points through the test. And so when a smartphone is jumping between transmitting these different channels, then another smartphone will detect the different power on the different channels, and it looks like high noise. It's actually just different propagation channel characteristics from different frequencies. And it gets even more complicated if both devices are moving. So this is moving across just 3 meters. And this was done with a conveyor belt moving very, very slowly. And it allows us to trace out these beautiful fading profiles, which, as you can see, instead of the power gently decreasing steadily with distance, as it should be, we're getting these really deep fades at various times. And this is all caused by what's called multipath interference. And this is when the signals in an indoor environment bounce around. And so the receiver picks up not just the line of sight signal, but reflections from the ceiling, the walls, objects in the room, the floor, people moving around, etc. They can all combine in phase and boost the signal a little bit louder, or they can knock each other out completely or almost completely. So you can get a little bit of a boost, but you can get a huge attenuation. And you only have to move a few centimeters to move out of a huge attenuation back to a boost again, because the wavelength is only 20 centimeters. So you only need to move, the wavelength is only about 10 centimeters. So you only need to move a few centimeters to change whether you're in phase or out of phase with these reflections. So a key thing is understanding that this variation is not coming from Gaussian white noise, thermal noise statistics at all. It's coming from fading profiles from multipath interference. You need to sample a healthy set of values. You need to do it from all the advertising channels, and you don't want to take the mean, because the error distribution is not symmetrical about the true value. A little bit of power can be boosted, but a huge amount of power can be lost. So it's a highly asymmetrical distribution. So there are better metrics in an emergency, if you're knocking something up quickly and just trying to push it out the door, then simple metrics like using the median or the max are better than using the mean. Certainly using the max if you've got rid of this Wi-Fi interference problem I mentioned earlier. But it's much better to generate a proper estimator using the known complicated error statistics of multipath. And there are plenty of books on how to use Rayleigh and Ricean error statistics to do multipath modeling correctly. Now, if you know what you're doing, you can simulate this stuff really well as well. And again, just please dive into my papers to see a bit more about simulating these things. But one of the great things about being able to simulate these effects and reproduce the kind of peaks and troughs and the periodicity of them and all the rest is that you can simulate what will happen in a whole bunch of different environments really easily. So if I was to try to go and find out what the fading profile with distance was like in buses and trains and open space theatres and lecture halls and restaurants and living rooms and foyers of hospitals and all this kind of stuff, it would take years to do experiments like that. But you can simulate to your heart's content in a few seconds on a modern laptop. Every single possible room dimension, every single possible material properties of the floor, the walls, the ceiling. You can produce an all-metal lift, you can produce a wooden lecture theatre, whatever you want. And so you can produce the actual spread and the understanding of the likelihood of being a certain distance from another Bluetooth transmitter and seeing high power or low power or the desired free space path loss value. You can also put people into your simulation if you like, and therefore get high attenuation values at close ranges. So on the left is line of sight open all the time. On the right is randomly drawn people blocking line of sight and stuff like that. And so with simulations, we can very, very quickly determine what we should use for the settings on contact tracing apps, way faster than we could do by trying to do manual experiments to understand what we should do with things like, should we use 1, 2, or 3 of the advertising channels? How much data should we gather, and how often should we gather data per measurement? What are the right metrics we should use to declare being close to or being far away from someone in order to declare exposure to the virus? critically, all of these things you can play with will set the false positives and false negatives of the contact tracing app. So false positives will annoy people because they will tell people to quarantine who were not actually exposed. And so too many false positives will lead to people not wanting to use the apps because they don't believe they're working properly. False negatives, of course, are much more serious because that's when you failed to detect that you were close to somebody when you really were. So false negatives can cause some serious problems in terms of people's health. So we really want to get these right by getting these settings right. And the best way to get these settings right is to do lots of trialing of all of the options in simulation. And I'm going to give another talk at some point in the future because there's another half an hour to go on simulating and the findings from them. So that's another talk for the future, but I can explain whether Matt Hancock was right or wrong with some quite simple analyses. The NHSX app made measurements every 15 seconds. The Google Apple Exposure Notification Protocol makes measurements at best every 150 seconds, at worst every 300 seconds. It seems to be a randomly drawn figure as to when it decides to make a measurement to see if there's another phone nearby. So obviously you've got a lot more data with the NHSX app approach. Certainly in dynamic scenarios, you're way less likely to miss an interaction if you're measuring every 15 seconds. Because the original NHSX app was using the traditional Bluetooth API calls, it automatically was randomly getting values across all 3 Bluetooth advertising channels. And the reason there are 3 is because that's the inherent multipath mitigation capability of Bluetooth. At the moment, the Google Apple Exposure Notification only uses 1 channel. It just takes readings on channel 37. They probably do this to try to save battery life, but it means they're more subject to multipath fades than using all 3 channels. In other words, you're more likely to be close to somebody with the Google Apple Exposure Notification and being told that you're really far away because you're in a multipath fade. And if you were hopping between all 3 channels, you'd hop out of that fade and you would detect a more realistic value for signal strength. And critically, the NHSX app were using a really impressive, very complicated Gaussian processes-based data-driven estimator for range. So complicated way of doing a good range estimate, giving the data that they could gather. The original Google Apple Exposure Notification was just taking the mean. And taking the mean when you've got multipath interference means that you will always estimate a value that's much lower than you should be estimating and would estimate if you gathered, if you used a different estimator, a better estimator. So hopefully the Google Apple Exposure Notification Protocol will move to a better estimator than this and move to one that's based on the statistics of multipath interference. And basically using lots of simulations and these settings, it was very easy for me to confirm quite quickly that the original NHSX app settings definitely would provide lower false positives and lower false negatives for contact tracing app, unless the iPhones are asleep 95% of the time, which of course was the problem, in which case that obviously means huge false negatives, missing loads of interactions with devices. And so hopefully these sorts of ideas will gradually migrate into the protocol that Google and Apple are using. But a lot of these things here, these decisions will be based on their desire to keep the battery life, to not impact battery life too much. So last mention for people wanting to do BLE contact tracing well, scan often, because that helps to reduce these problems of false positives and false negatives. So one of the other challenges of just using Bluetooth is that we've chosen 2.4 gig as our Wi-Fi and Bluetooth communication scheme for a good reason. It punches straight through building materials very well. And so if you've got a Bluetooth device just 30 centimeters away from you in the same room, like I did here, you'll get a high signal power. I then went 30 centimeters away from it to the other side of an interior brick wall that was about 10 centimeters wide and measured almost exactly the same power. And that's because Bluetooth just sails through dry brick relatively easily. I'd have got, instead of 2 dB of loss, I'd have got about 15 dB of loss just by putting my body in the way instead. So this is one of the big challenges. Bluetooth isn't giving us a good estimate of whether we're in the same airspace as someone else. It's just telling us whether we are within a similar latitude and longitude to them, but there could be barriers in the way. So to get around this, we need to bring other sensors to bear. And because coronavirus is being carried by breathing, coughing, and sneezing through the air, it's a good idea to bring some sensors to bear that help to confirm whether we are in the same airspace. So measurements from the barometer could be compared between the phones. This would help to confirm, for example, if I'm sat inside a warm, dry environment and outside it's much colder and much wetter, and if someone's through the pane of glass the other side of the window, there'd be quite a difference in the barometer readings, for example, although the Bluetooth signal strength would be very, very high. You could also record a short fingerprint of audio, so you could use the Bluetooth to basically trigger that both devices will capture in the same moment, say 1/10 of a second's worth of audio from the microphone. You can then transfer those to each phone and compare the spectrum, the frequency spectrum of those audio fingerprints. That would confirm if both phones were experiencing the same audio environment. So my phone here with me now would have the fingerprint associated with me speaking, whereas one just outside that double glazed window in front of me there would not detect any of that spectrum, and it would have bird song and road noise and things instead. So this is a good way to confirm if you're in the same room or not. And this will be a big problem with things like people stuck in traffic, that there'll be lots of exposure notifications going off between phones between different vehicles in stationary traffic when the people have actually not come into contact with each other at all. You can also do an ultrasonic ping between the devices instead of a Bluetooth ping, and more on that in a moment. But one thing I quickly wanted to note about cars stuck in traffic, one thing we have to be particularly careful of here is actually about the propagation characteristics of electromagnetic radiation between vehicles. So this is a well-researched topic, and so some features I'm about to explain are very well understood and are going to be a problem. If you take panel vans like this one, and they're quite common, as you can see, there's about 5 in this photograph, and I just arbitrarily grabbed a photograph off the internet, and there's quite a lot of panel vans in this one. They're obviously a heavily all-metal construction apart from the glass frontage, and these act as a bit of a lighthouse to electromagnetic radiation. So they actually project a fan beam out the front, which is giving you better than free space path loss. In other words, this driver here with his Bluetooth COVID tracking app smartphone, he's effectively projecting himself about 5 meters outside his car into this one and next to this cyclist and so on, because the energy that should be going in all the other directions in his panel van is being carried forwards and to the sides, boosting his apparent proximity to these people. So panel van drivers will be driving around the country permanently projecting themselves as if they're in the seat of the car in front of them. And so there'll be huge numbers of false positives from these sorts of vehicles. So we need to be really careful with using Bluetooth. So we must use other sensors to confirm that 2 vehicles are actually in the same airspace. One of the most interesting apps I've come across is this company called Novid. They are using ultrasound instead of Bluetooth. And due to the physics of that, they can measure to a few centimeters the range between 2 phones. So the ranging estimate is much better than with Bluetooth. But because ultrasound is being carried by the air itself, this automatically is also a good way of confirming you're in the same airspace. So ultrasound won't go through glass, it won't go through walls, floors, ceilings. It will dramatically reduce the false positive problems that we'll get with Bluetooth, of Bluetooth going through construction materials and glass. So I really hope other entities will start using ultrasound as well. And take a look at Novid, they're a really interesting group. They showed me this, which I've never seen anyone else work on for contact tracing. This is like a rainfall radar for coronavirus. So it's actually showing you when coronavirus is coming towards you through your network. So all the current COVID tracking apps are aiming to alert you that you have been exposed to it. What this does is the Novid app over time builds up a network anonymously of who you're connected to through, let's say this is me, and one step away might be my wife, and then someone my wife works with, and someone they play squash with, and someone that person goes to the pub with, and someone that person goes to church with, and someone that person works in the hospital with, or whatever. And what this is showing is, as people far away in your network start to actually get coronavirus, this warns you that it's kind of coming to you, like rain on a rainfall radar. And you can see that you're getting to kind of 3 or 4 handshakes away from coronavirus, and you can make a decision that you're not going to go out and interact with people. You're not going to go to squash. You're not going to go to church, etc., because you don't know who it is through your network, but it's coming. So I think that's really cool, and I hope other contact tracing apps make use of a networking effect and start to build in this forecasting capability as well. The last fight I'll touch on is simply location. Fundamentally, as I mentioned at the beginning, contact tracers traditionally use knowledge of where you've been as part of their understanding as to whether other people have been exposed. The Google Apple Exposure Notification Protocol prevents access to location. You cannot build a contact tracing app with the new protocol that also stores location. Now, they've done this as part of a privacy drive. They're sort of forcing privacy to be part of their protocol to the extreme that they won't allow you to log location at all. And of course, that for some is simply not workable. And so we do have this great spread of countries that are choosing to use different technologies. Some are using the new protocol, some are using Bluetooth, but not the new protocol. And some are, in fact, it's roughly equal splits. Many are just going for location-based, and they're just passing location information to traditional contact tracing systems. And there's a whole bunch of other things as well. So in summary, I think there's an awful lot still to improve in this space. We're quite a few months in, and we've got quite a few months still to go. Hopefully the Google Apple Exposure Notification Protocol will steadily improve. There are lots of improvements they can make. One of the biggest challenges is basically understanding what the internal priorities of a large company is versus what other entities' priorities might be, because we will inevitably always have this clash if different entities are deciding different things are the priority for contact tracing. It's obvious to anyone that's ever worked in location and sensor fusion that you must combine various sensor technologies to get the best possible performance. And so this will come combining more than just Bluetooth in order to get the best possible performance and minimize those false positives and false negatives. My personal belief is that it should be down to end users. So of course you can, in principle, build an app that has all of these things available for the user to choose when they install it and turn on and off. And I think that's the right way to go. Have the default settings, set maximum privacy. If you like, even make it quite hard to change those settings, but still give the end users the rights to decide what they want their trade-offs to be between privacy and battery life and the well-being of themselves and their loved ones. And at that, I will leave it there and take any questions. Thank you very much.